change your location.
Yeah.
Make it perfect, huh?
Yes.
Okay. So are you selling this thing?
I'm charging everybody $10.
That's why they are not here?
They're just late.
For electrode, we've been talking about working electrode. So what about the other half? Is the reference electrode. So here is a most common reference electrode called SCE. So remember the name, saturated column electrode. Okay, so remember your candy bar or something. And remember the composition. So be able to draw an electrode like this, with a tube. Basically, you will need a conductor. So in this case, it's a platinum wire. So this is not going to participate in the reaction. So the wire is going to stick into a paste composition of all these mercury chloride, and KCl. So the three as a paste, so it is conducting. So remember, there's a small pinhole here for interaction between the internal paste solution, is a paste, and external saturated solution. So what's saturated in here is KCl. So it's not solid, it's a solution. So it's K plus and Cl minus. It is saturated, therefore the concentration is a constant. When this concentration is constant, then the ion mobility inside will be a constant, and therefore the potential inside is a constant. Okay, then here's a filler hole to make sure you have this internal solution filled. So it is not just water. Some people thought that, okay, when there's a hole to fill in a liquid, I put in the ionized water. No, that's not. Or some people say that, okay, let me put in buffer solution. It is not buffer solution. So it's KCl. Remember that, because in the real world, a lot of people still mistaken using buffer solution, page 7. Okay, so here's a fiber for this solution in touch with your sample solution. So looking at the composition, then this is a half reaction. So your mercury, your mercurous chloride, and you have KCl, the Cl minus. So this is a half reaction to describe this saturated standard reference solution. Jeffrey is making so obvious. Taking a picture now. Okay, and remember this half reaction. Okay, the equation. Once you'll be able to write this half reaction. Actually, you can look it up in the potentials table. Okay, as long as you remember this kind of thing, I have mercury. When mercury in touch with KCl, it's going to give you mercurous chloride. So as long as you may remember that and that, this is automatic. Then the potentials table, you just make a match for the equation. Then you should be able to write this Nernst equation. Okay, so this is an experimental potential. This is a table value. Experimental potential depends on the concentration of KCl. So this is saturated and therefore it's constant. Notice is a chloride to the power 2, then this is saturated, so it is a constant. So when it's a constant, then it turns out that the potential is this one. This is an experimental potential. This is a constant, okay? Yes?
Okay, for the homework, what they did was instead of putting it 1 over chloride squared when it was saturated. Oh, no, when it was saturated. Oh, yeah, never mind, you flipped it. Okay, never mind.
I can read your mind.
I know.
That means your low C is exam number 2. Is this going to be an extra credit?
Will there be extra credit? Yeah, I know, that sounds good.
Okay. Now, for the glass membrane electrode, it is a working electrode. Okay, so there's a working electrode. In combination with the SCE, then you have a complete setup. So the working electrode are long. Now this is a proton specific. So the lead wire is just a conductor. It doesn't participate in the reaction. It is connected to the silver wire, which participate in reaction. Okay, so silver in contact with HCl, so silver in contact with Cl, then it becomes silver chloride at the surface. Okay, then a glass composition is going to be proton sensitive. So this is a key thing. It is the glass composition to make the proton. There's a affinity for proton because of the composition. So the proton is H+, so the cation is going to line up along the glass membrane. Then you have the internal ion line up against the external proton. So whenever you measure a difference in the potential between the two, internal potential versus external potential, that is how much ions line up. Whenever there's a difference, then you read a delta E. Then delta E is registered. Okay? So remember this composition. Okay. So for the potential, what do you mean by potential? Let's look at the diagram here. So here is your working electrode. Okay, with the silver chloride, HCl, with this concentration. So you're going to line up with a potential because these are ions. So there is a line up for potential. Now on this side, it will be the reference electrode. So there will be potential line up as well. So because this is ion, this is ion. Okay, so there will be a line up here. And okay, then whenever you have potential, so externally you have ions, internally you have ions. So whenever there's a difference, then there's delta E, difference in potential. So what you call here, this is your junction, right? Your sample and internal solution, then there's a junction potential. So what you measure will be this junction potential. However, internally, you also will have a junction potential. So the boundary is called your junction. So the internal junction potential, though, you want it to be constant. You don't want it to change so that you can measure this delta E, right? And similarly, you don't want the internal junction potential to be different in here. So this is a junction. So overall, whatever you mean by junction potential is just simply the difference between the boundary, your ions here, your ions here. For example, you have a boundary like this, okay? So you have the internal boundary. This is a H plus. This is a H plus here. So line up with a minus along the way, H plus. So you have the Cl. Cl is minus. Cl minus here. Then the H plus is going to line up here. So you have a difference. Then the H plus is going to line up opposite to Cl minus. So the H plus here, Cl minus here, H plus here. So you have, okay, so this line should be drawn up here instead. So you have internally, you have the H plus and the Cl minus line up along the membrane, and then externally, you have the H plus line up as well. Okay? So it should have drawn like this. So there's internal, then external. So you have this kind of line up, and therefore, so you have a delta E that is measured. Okay, as you can see, how many junctions are there, right? There will be, I number them, 1, 2, 3, 4. So all these 1, 2, 3, 4, these are the junction potentials. Okay, then you want the internal lineup. So the 1, 2, inside, 3, inside, 4, inside here. Those ions to line up should be a constant. Okay, you want them to be constant so that you can measure the difference. Now, however, it all depends on the ionic strength here. So when you sample ions, the ionic strengths change, then the internal potentials, the internal ions line up will be different as well. While you want them to be the same. But then whenever your ionic strength is changed, then your internal lineup will be changed as well. So that appears to interfere with your measurement. Okay? So now you are set up for the next slide. So do you agree with this first? Do you get the meaning? You want the internal. So from this boundary, the internal lineup of ions to be constant. Okay, then start from number 3, this boundary, the internal ions lineup to be a constant. Then you can measure the change in the ions in your sample solution. However, your unknown solution is an unknown composition of ionic strength, all sort of ions. So when you throw that sample in, then all of a sudden all the internal ions arrangement will change as well. So the internal junction potentials will change because of attraction and repulsion from the outside. It doesn't matter whether you have selectivity for particular ions like proton. Okay, you have so many unknown ions, repulsion and attraction, that you change the internal lineup of ions as well. Okay, so electrochemistry basic limitation, will be understanding of the junction potential. For electrochem, so you can talk with Dr. Che, he's an expert on that. What is your major problem? Then he would tell you the junction potentials. Okay, then